That's the first question. What is an ellipse? Go. An oval. A lot of people want to say that, right? Yes, an oval. What's an oval? A stretched. Oh, no, you can't see. There you go. My handwriting is really not very pretty today, so it probably works out okay for you. A stretched circle. So it's like you take a circle and you like step on it, right? Not all the way, but you step on it so it gets a little squishy, or it can be squishy the other way, right? So, those kind of shapes, those are ellipses, okay? I like analogies, and the analogy that I think I've told you already before is that an ellipse is to a circle what a rectangle is to a square. Do you guys know what a rectangle looks like, right? And a rectangle can, if it has all the same size sides, be a square. You with me there? Yeah, they're all quadrilaterals. Miss Geometry Lady today, yeah. A circle is a very specific kind of ellipse. It's the kind of ellipse where everything is all the same length. If you have taken geometry or you have talked about circles in some math class, you may have defined a circle. Does anybody know what a circle is called? Or what, not called, but what it's defined as, or how you define a circle? What is a circle? Maybe I should have had that out there too.
It has an equal radius all the way around from.
Yeah. So a circle has one dot in the middle, right? That point is called the center, and a circle is every dot that's the same distance from that radius. So this is not going to be a perfect circle, but you get the idea, right? Every point an equal distance from, now I'll draw the center so that it looks a little bit better, from the center. So this distance and this distance and this distance, they're all the same. Do you remember when you were doing your lab yesterday with the ellipse? Did it have one nail in the middle and then you stretched that all the way around? No, it didn't. What did it have, David? It had two nails, didn't it? So it's kind of the same idea. You have two dots. So instead of calling them the center, do you remember, based on what you read, what those two dots are called? Starts with an F. The foci or the foci, right? They're each called a focus. Okay? So you've got two foci or two foci, and you took, instead of having one thing that's all the same length around, you had a string that when you stretched it, and I don't know if you thought about this, this is kind of the funny thing, as you stretched that string, it was always the same distance if you add these two things together. So let me show you what I mean by that. So if this is my ellipse, this distance plus that distance is the same as this distance plus this distance. Are you with me there? Yeah. Does that kind of make sense? It's the same as this distance plus this distance, okay? That's what the definition of an ellipse is. The distance from each focus, if you add those together, has to be the same all the way around. That's what an ellipse is, okay? Cool. I'm so glad to know that. Why? We're not in geometry class. I used to teach geometry, which is why I love this stuff. We're not in geometry class. You're like, I didn't sign up for geometry. I signed up for earth science. Well, maybe you also did. You're like, I just get double the geometry today, right? Why are we doing this today? First period in a science classroom.
Because it helps us understand the way things move.
Because it helps us understand the way things move. In particular, what things are we talking about? What's moving? I hear little grumblings of things. Why do we care about this in terms of our solar system?
Because that's how our planets orbit.
That's how our planets orbit. Yes. So we're going to write this down, and then I have to point something out to you that's kind of interesting. So what does it have to do with our solar system? All of the planets orbit the sun in ellipses. Okay? Their trajectory or the shape of their orbit is always an ellipse. Quick question. Is a circle an ellipse? Hayden says, try again because you said it right before. Is a circle an ellipse? Yes! Yes, he says absolutely. Do you remember I just said that a square is a rectangle, right? And a circle is an ellipse. It's just a very specific kind of ellipse. Okay? So who is the person that threw this out at us? Who is the person that made us think about ellipses? He may have had some poor character decisions we've learned yesterday, right? That was the big scandal that we learned about yesterday. Can somebody give Jacob the 10-second version of what we learned about the scandal from 15 whatever?
Kepler's a murderer.
Kepler's a murderer. That's the short version. That was like less than 10 seconds. That was like the 3-second version. Now, do we know for sure?
No.
We don't know for sure, but there is pretty strong evidence. There is a motive, right? There's a motive, and there was some bad blood between them. Okay? Kepler, who, Liz, do you think that Kepler may have done away with? What was his name? Brahe. So Jacob's like, oh yeah, we talked about that Brahe guy earlier, right? He's the one with the nose, or lack thereof, the metal nose, right? I really hope you guys, someday you're going to be in some museum somewhere in maybe Denmark or something. I don't know why you're going to find yourself there, but you're going to be walking through this museum and you're going to see the nose. And you're going to say, what?
Oh my gosh.
And then you're going to say, oh my gosh, I need to find Miss Carmeling. And you're going to look me up online. You're going to find a way to get a hold of me and be like, I just saw his nose. And then you just send it to me, okay? Whoever does that, like, that's awesome. I want it because that's so interesting. So, Jacob, the short version of the story is Brahe had no nose. He got in a duel when he was 20. Awkward. So he had like a copper nose and he had all these different kinds of noses, and one of them's in a museum somewhere. We want to find it. So that's like our goal for life.
Field trip.
No! You just gotta happen to find it. Come on. Where's your sense of adventure? All right.
We can have
So Brahe has no nose, but he does something that's helpful, right? What else is Brahe known for besides the lack of a nose? What did he do scientifically?
He liked to take data, but he didn't organize it.
Yeah, so he took tons of data, right? Tons and tons of data, and he did organize it, but he had no idea what to do with it. He's like, I don't know. Then there was this other guy, Kepler, right, who didn't want to take the data, but he wanted to figure it out. He's like, hey, Brahe, you've got lots of good data. I'd like your data. And Brahe said, no. And he said, oh yeah? And then something happened. He had indigestion, mercury poisoning, and Kepler ended up with the data. Well, that's good for us, right? That's good for us because now Kepler was able to tell us that everything moves in an ellipse. Prior to Kepler, if you look at the front of your As the Worlds turn sheet, if you wanted to do that, if you look at all those people and everything that you wrote down about them on this first page, Aristotle, Jafar ibn Muhammad, Copernicus, Brahe, they all believed, whether the sun was at the center or the earth was at the center, they all believed that things moved in perfect what? Circles all the time. All of these people and everybody before them believed that things moved in circles. Kepler's big deal, well, one of his 3 big deals, there were 3 of them, one of his 3 big deals was to say that nope, in fact, the planets move in ellipses. Could some of them move in circles? Because a circle is a what? An ellipse. Are we okay here? All right, awesome. So I want to show you this real quickly because I think it's kind of interesting. Let me see if it pops up here. Sweet, it does. So this is like from some, I don't know, mathy math website, but I just wanted to show this to you because I want to point out that this is kind of an interesting deal. I'm hoping that this will work here. So this is an ellipse. These 2 F's stand for what? foci, or this is a focus and this is a focus. And hey, oh, by the way, what is at one of the foci of the ellipse? The sun, right? So if this is the Earth, the sun is here or here. It doesn't really matter because it's all symmetrical. The thing that I want to point out to you is that those foci can move. Okay, so if you go like this, you put the foci right on top of each other, then you have a what? A circle. And oh my gosh, a circle is an ellipse. What? But then you can also go, so you can get these really, really big ellipses. Now, if you go downtown and you ask somebody to draw the orbit of a planet around the sun, especially one of those really far outside planets, and they have this idea, they might put it like this so that the planet goes way out here and way back in, okay? And this ellipse in this elliptical orbit. But what I really wanted to show you is that that's kind of not true. It's a little bit interesting, so I just wanted to show you. The thing that tells you how squishy the orbit is this thing called eccentricity. The smaller the eccentricity, the closer it is to a circle. Okay, so an eccentricity of 0 is a circle because a circle is an ellipse. We know that. So if we look at Earth, here and there are lots of bunch of other numbers, but the one that I care about, here's Earth, and there's our eccentricity. That is pretty darn close to what? It's pretty darn close to 0. And oh my gosh, Venus, what? That's really darn close to 0. The biggest thing on here is what? The biggest eccentricity is Pluto. So I'm just going to write those numbers down. So Earth had an eccentricity of 0.0. I'm going to call that 0.02 because I'm lazy. And Pluto has an eccentricity of 0.25. Just again, because I'm kind of lazy. I just want to show you what those look like on this graph because it's interesting. So do you see where it lists eccentricity right there? Yeah. Okay. So the eccentricity of this ellipse is pretty big. It's 0.91. It's almost 1. Let's take a look, though. Tell me when we get to Pluto's eccentricity. Because I don't remember. What does it say up there that it is? 0.25. Are we there yet? Are we there yet? Are we there yet? Oh. Right? It looks pretty darn close to a circle, doesn't it? And that's the most squishy of an orbit that we have of the planets or planetoid objects in our solar system. Okay, let me show you the ellipse that is our Earth. What was it? Point what? Can I get there? Oh, I skipped it. There we go. I'll just leave it at 3. That's the ellipse that is our orbit, okay? The distance that we are from the sun, because remember the sun is at the purple dot, that we are from the sun here versus here, is it very big? Is it very different? Not in the grand scheme of things. I just want to point that out to you because I don't want you to think that all of these orbits are in these really, really, squishy ellipses. Does that make sense? Okay. Just one of those, it's a common misconception, and I don't want you to have that misconception. I want you to be able to, when the people stop you on the street and ask you those random questions saying, they're not going to know anything, you're going to be like, I got this. And you're going to be like that outlier, that person that actually knows the answer, right? That's you. What's that? I know it's for like a YouTube channel, like a late night TV show, or I know, that's what I'm saying, right? Yeah. So now you're going to be the person that's going to totally throw off all their data.
They're usually really wrong. No.
Right. Well, and that's the thing. So probably all the people like you guys won't actually make it on the TV show. Yeah.
Or the funny ones that are
all right. Questions about this before we move on? Okay, pull out that green sheet you got. So this is the one that we started yesterday. You did the first law yesterday. Hey, planets orbit around the sun in an elliptical shape with the center of the sun being located at one focus. That's cool. You did that yesterday. Did we answer this post-lab question yesterday? Yeah? Trace the shape with your finger. Imagine that the path of the planet moves around the sun. Is the planet... Oh, you need one? Yes, absolutely. Here you go, my dear. Yeah. Is the planet the same distance from the sun the entire time? The answer is it's not exactly the same, right? So it goes further and closer and further and closer. But as I showed you before, it's not that much further and closer. We'll do the math another day to figure out how much further it is. Once you've got that done, I want you to turn it over to the back. Okay? We've got 2 more to do today. I think we can get them both done. Kepler's second law is one that you're just going to kind of read through. I want you to just work with your table mates, okay? Talk it through with your table mates. You're going to read it, look at the picture, answer the questions. When you get done with it, you're going to when you get done with it, you'll come up and get the next sheet, and I'll have you guys just work at your tables with this today. Does that sound good? All right. Go ahead and get started on the back. Take a look at it. Read it.